Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 4, Further Network Problems, and this is video 4.1, Matching Problems. So firstly, just a reminder about matching problems. They can be represented by bipartite graphs. So for example, this bipartite graph here, we've got four sets of nodes A, B, C and D, and another four sets of nodes 1, 2, 3 and 4. So they form two separate groups, and there are possible matchings there between each of between some of the nodes in this group and some of the nodes in the other. So what this could represent possibly could be four workers A, B, C and D, and four tasks, and the matchings show whether or not a particular worker is able to do a particular task. And ideally we want to find a matching, so we want to match each worker to a task uniquely, so that each worker has a task and each task has a worker. Another way of representing this problem is in a table with a cross indicating a possible association of a task with a worker. So what we're trying to do is to use some of these possible, what on the graph are these arcs or these crosses, choose some of them so that there is a unique pairing between each of these nodes and each of these nodes. And ideally, if we're thinking about this now as a maximization problem, maybe in some situations it's not possible for a unique matching to be found, in others it will. But if we try to maximize the number of unique matchings, then that might be one approach to solving the problem. So what we'll do is we'll introduce a variable for each of the possible matchings, each of the possible associations between the two groups of nodes, and we can label these variables using the coordinates in this grid. So for example, this one, the variable b3, will indicate whether or not this arc is included in our resulting graph. In other words, if this association is going to be part of the matching that we choose. Now, because we've got 7 possible pairings, each one will take a value of 1 if it's going to be included in the matching, 0 if it's not. And what we want to do, because we're trying to get to a situation where we've got everyone is matched with each worker is matched with a task, for example, so we're trying to maximize the number of these things which are included, subject to the constraint that only there'll only be one cross in each row and one cross in each column, so that the pairings are unique. So if we can achieve that, if we can maximize the sum of those variables within these constraints, then potentially at least we'll have a unique matching of every node to every node in the other group. If it is possible for that to be done, then this maximization will find it. So quite straightforward this then. We don't have any numbers associated with these variables, so it's just going to be a case of adding them all together. So the thing we want to maximize is A1 plus A4. So we're just adding the variables which are there with the crosses in the table, and so on, like so. And then the constraints, as we say, come from the fact that we can only have one cross in each row and one cross in each column. So firstly, looking along the columns, we've got A1, A4. We can have at most one of those, so that means that A1 plus A4 must be less than or equal to 1. We'll do the same thing for the other rows, like so. Notice we have this one at the bottom there because there's only the one cross in this row anyway, but we'll still include that constraint, d3 less than or equal to 1. And we need to do the same thing now for the columns, so that gives us A1 plus B1 is less than or equal to 1. There it is. And then for the next column we just have C2 less than or equal to 1, and then we keep going, like that. So notice, for example, this one that comes from this column with 3 crosses in, and the other thing, of course, is that all these variables have to be either 1 or 0, so they're all binary variables. So there we are. That's the formulation of the problem in terms of a linear programming problem. So having put that into our solver, we can see that it's found a solution. Good news, the objective function is 4. That means it's definitely found 4 arcs, so that means it has matched every node here to every node here. If that had been less than 4, it would have meant that it wasn't actually possible to do a complete matching. If we look at which arcs are included, then we've got A4, B1, C2 and D3. So it's this one here, A4, B1, C2 and D3. So there we can see how that's worked there. And of course, if we were looking at this on our table, we've got this one, A4, we've got B1, we've got C2, and we've got D3 there. So that concludes video 4.1, matching problems. Next video, 4.2, we're going to look at allocation problems.